All right, hello everybody. Just about 2 o'clock Eastern time now, so we're going to kick things off here. Thanks for coming back for another webinar. Today we're going to cover hole making and thread milling, a topic a lot of people have questions about. My name is Jeff Rossio. I'm the manager of digital marketing here with Harvey Performance Company. I'll be moderating this today and be in the chat under the Harvey Tool username. And I have Don Grant with me, our national application engineer. This guy knows more about drills and thread mills than probably anybody else I know. So it's going to be a great presentation today. I'm really looking forward to it. Hopefully you guys are too. With that being said, questions we will have at the end. If you throw questions in the chat, we'll be able to see them and answer all those at the end. And I will let Don take it away and talk to you guys back when we have questions.
Well, thank you, Jeff. Appreciate that. And I appreciate the kind words. And Jeff is correct. I do know a lot about drills and thread mills and how to use them because I probably broke enough of them. And that's pretty much how we learn. So again, thanks, Jeff. Appreciate the introduction. Also appreciate everybody taking the time this afternoon to join us for another edition of As the Cutting Tool Turns, I've been calling it, so to speak. Jeff loves that name, by the way. But today we're going to talk about hole making and thread milling, tips needed to master your craft. So I do have a lot of experience in round tools and drills and thread mills. And so basically just want to bring you through all those things that kind of help make that a little bit easier for you guys to manage. Trying to run through the slides here. A little bit of technical difficult with actually trying to get the slides to actually run through. So just give me 1 second here. I know things have been fairly smooth up to this point. There we go. All right, so anyway, just a quick introduction. Like I said, we are the Harvey Performance Company, which includes Harvey Tool, Helical Solutions, and Micro 100. Everybody kind of knows us for Harvey Tool with the miniature tools, specialty cutting tools. It's going to incorporate a lot of the drills we're going to talk about today, a lot of the thread mills, Helical Solutions, your high performance material specific tools, and then of course Micro 100, which is your specialty miniature turning tools, and thread mills and drills too as well. A little bit more general purpose in that area, but also kind of embed some of the tools we're actually going to talk about today. So if we jump into the next slide here. I don't know why this isn't clicking. There we go, hole making. Again, introduction on my end. My name is, like I said, Don Grant. So just want to give you a little bit of background on myself. So I actually started right out of high school actually making drills. So when it comes to hole making, it's a little bit dear and near to me as far as that goes, because I actually started making drills for a company called Precision Twist Drill back in the late 80s. So I have a lot of experience on geometries and tools and how to actually apply them and use them. So we're going to jump right into this as far as hole making goes and start talking about some of the advantages. So first, let's talk about the twist drill. It's one of the oldest known and most used tools that we have in our arsenal. It's also one of the most abused tools because of it's the least understood. Seems like a simple design, but it is kind of the least understood. Over 70% of chips generated on the shop floor come from your drills. It's actually one of the highest and fastest metal removal tool that you'll have in your arsenal. So let's talk about a drill's journey real quick, just to give you a little bit idea. In 1820, they actually started drills way back then. They actually came out with the carbon steel drills, had a lot of carbon in them, would heat treat them, and use those as a drill. In the 1900s, they kind of switched over to high-speed steel twist drills, and then added cobalt for more hardening and red hardness too. So they would actually be able to take a little bit more heat. In the 30s, they came in with carbide tip drills where they just put a little carbide insert on there. In the 80s is where solid carbide came about. And then Past that, we started adding coatings and adding different varieties of substrate to actually add strength to the tools. So this is my idol, the fact that I'm a drill guy. So Stephen Morris, the general purpose twist drill was patented by Stephen Morris in 1863. And if anybody knows the Morris Cutting Tool Company, that's kind of where it started. Drill's journey actually started with the Morris Cutting Tool Company. So that's just kind of a little bit of history on this before we actually dive into a tool. So now let's get to the meat and potatoes of a drill and how to use this. I think that's pretty much why everybody's on this call. They want to understand how to use a tool a little bit better. So let's understand all the features of a tool. So simplicity in design. A drill's geometry serves three major purposes. It's real simple if you think about it. It needs to make a chip, it needs to hold a chip, and it needs to evacuate a chip. So first let's talk about actually making the chip and what that looks like. So the drill's point geometry is very critical. It's very important to actually making sure that the chip that is formed is adequate for the material you're actually cutting. Now, when we go through this whole presentation, I want to just kind of preface it and make sure that everybody's aware that what we're going to teach today and what we're going to talk about is really not as specific to different materials and different drill geometries. So this is an understanding of how these tools work and how to use them. But when you actually start running up against different materials and different drills, some of these things might need to be tweaked and changed a little bit. So the drill point geometry is very critical. The point's the working end of the tool where the chip is actually going to be made. The chisel edge is the first point of contact with material. So every drill has a chisel edge right in the center of it. That's what's going to touch the material first. The chisel edge creates the major thrust force or thrust force. I think we forgot an H there, but actually you got to trust your drill to get it done. So that's not entirely incorrect. But the thrust force from the drill is actually coming from the chisel edge. The chisel edge angle and its accuracy, along with the cutting lips, which is the outside of the drill, actually control the whole positioning, size, and straightness. So selecting the correct point geometry for your application is key to the success of actually drilling successful holes. So like I said, this is kind of a depiction of more of a general purpose end of a tool. That this is the chisel edge we're talking about. If you take a look at the end of your tool, that's the chisel. Now that comes in different web thicknesses, lengths, and sizes, but it's what's creating the majority of the force and the thrust force on the drill. The cutting edge is actually the straight line along that connects to the chisel edge. That's what's actually cutting and generating a chip on your material. We have a rake angle, which is actually shearing the material, running it down the flutes. You have axial rake, you have radial rake, and then all drills have a clearance on them. If we've ever been in a shop, took a drill to a bench grinder, which I'm sure we've all done, we all want to make sure we regrind the point, make sure that chisel edge is on center, but we have to put clearance on it. Because if we don't put clearance on it, it will not drill straight and we'll have all kinds of problems as far as hole accuracy. So as we're making this chip, high thrust forces, torque, and bending motion occur during the drill process. We're putting thrust on this. Two things with a drill, thrust force and torque. Those are the two things we're looking at. So we have a lot of thrust force that's generated from the chisel, and we have a lot of torque that's generated from the cutting edge. So if you look at this picture, a chisel of 10% creates 70% of the thrust force. Okay, so if our chisel on a half-inch drill is 10% of that half, so 50 thou, that's creating 70% of that thrust force. So if we go to the next slide and we actually take a look at where this is, a drill with 10% of the core or web diameter, 70% of the thrust force, but if we split that or if we web thin that tool, we can reduce that by 40%. Thrust force is key when you're actually drilling a hole. So if we split the end of the drill, we can decrease the feed force to 30%. On the next slide, if we take a look at that, we can actually look at the picture on the right-hand side. This is a split drill. This is pretty much everything you're going to see on a Harvey Performance drill. Some of the drills on the Micro 100 side are more of a straight chisel edge, but what we do is we split the end of the tool, and most manufacturers will split the end of the tool. This creates a lot of things going on for the drill. Number one is we're eliminating the thrust force on that drill by actually splitting it, which gives you a primary cutting edge and it gives you a secondary cutting edge. That's number one. Number two is we're helping self-center that drill. That drill is going to self-center a little bit better by splitting that. Okay. And number three is we're actually breaking up the chip. It acts like a chip breaker so we can get manageable chips. Remember I said a drill is broken down into three categories, right? Make a chip, hold a chip, evacuate a chip. So we need to hold a chip. So if we got to hold a chip with a drill, we got to make sure the chips are manageable. And that's part of this conversation we're going to have today, is to manage the chips. Also, if you look at the picture on the left, this is drill speed along the cutting edge. So when a drill's spinning, it's not like an end mill. It's not cutting on the peripheral, so therefore our surface footage can be constant. In the center of a drill, our velocity, our surface footage is actually at zero. As we start working our way out to the outside of the tool is where we actually get our surface footage, actually get the surface footage we're trying to get on the drill. So what we're creating on the center of the drill is a lot of thrust force, right? We're pushing, we're plowing. So what we need to do is get a point geometry that's thinned well enough, that takes the force off the chip, that breaks the chip up, manages the chip, so we can reduce all that force on the end of the drill, because what we don't want is we don't want all that walking. We don't want that movement of the drill. You want to reduce the thrust force. You want to reduce the amount of force on the spindle, and you want that drill to just perform by using its cutting edge, by using its primary, its secondary, its web, make a round hole, hold the chip and evacuate it. So if we run to the next slide, next thing we got to do is hold the chip. So we need to manage that chip. We got to hold that chip. So our flutes that are generated in there do a great job of holding the chip and evacuating the chip. The first thing we need to do is obviously make a chip that's manageable. We have to make a chip that's manageable. Very important to follow this process, that if you don't make a manageable chip, we're going to have problems as that chip enters the flute valley and gets clogged up. So we have a web diameter. In an end mill, it's called a core. In a drill, it's called a web. We have our company. I'm a drill guy, so when I hear somebody call a drill web a core, I get a little antsy and I start shaking a little bit. But usually it's because I had too much coffee. But besides that, so we have a web on there. So our web thickness is really going to dictate how much flute room we have in there. That's number one. But also the flute shape. There's different things you can do with a flute on a drill to make sure the shape of that flute and the heel and the back of that can accommodate the chip that you want to manage. This is why it's very important when you're looking at a drill. If you want to get optimal performance out of a drill, you're looking at material-specific drills. You're looking for drills that are for hardened materials. You're looking for drills that are for pre-hardened materials. You're looking for drills that are for aluminum materials or softer materials. Because what that does is, even though you might learn something from this, you might understand it, is you have to trust your vendors that the geometry they put on the tools are there to hold and manage your chip. Now, there's an application involved there. Don't get me wrong, and we're going to talk about applications, right? I'm talking right now about geometry. We need to design a tool that's going to make a chip for the material that's correct, which means we're going to split that, we're going to reduce the forces, we're going to break up that chip, then we're going to hold it. We're going to put the flute design knowing what that chip looks like, because every chip for every material has certain characteristics. We're really trying to manage those chips and hold those chips. So it's important to design the flute to accommodate the point. Now, if we go to the next slide and actually look at evacuating the chip, this is where we have these flutes. We have different things going on that we want to actually help evacuate the chip. So let's just take a look at a drill that usually in common, and I'm going back and years here, is commonly 3 different helix angles is kind of the standard for drills, whether it be high speed. We talked about high speed steel drills, and I'm sure there's a lot of people out there using those, or cobalt drills. Then you got carbide tip drills. Well, the helix angle is designed to manage certain types of chips. So we got 3 different helix angles that really are conducive to drills that are, you're going to see standard. There's more than this, but they kind of break down to a standard overview. First, there's slow and low helix, which is a little bit more for your cast irons, a little bit for your brass, the ones that are going to break up a chip that you don't need to evacuate as well. You have common or medium helix, I call them, which is pretty much standard in today's world on most carbide tools, because we're using different geometries to get the chips up the flute. So a standard or a common helix is what you're going to see on most tools. And then we have a fast or a high helix, which is good for aluminums, good for softer materials where we want to grab that chip, we want to pull it up as quick as possible, and we want to evacuate it out the hole. Now, when you're looking at helix angles, again, go for your recommended vendor for material specific. That's great. But this is where I said there's a window. So if you're running in a vertical machine or you're running in a horizontal machine, these things can change and they might work differently because gravity's on your side right now. So there's a lot of variables in the helix angle, but this is the main thing that's going to evacuate a chip. So this is the big question, and these are the things that people want to know. To peck or not to peck? That is the question, right? It's a little bit of, what is that, Shakespeare I threw in there. But this is a big question, and this is a lot of our application engineers on our team, because of my experience with drills, are always calling me. And 9 out of 10 times when there's an application with a drill that somebody's having issues with, it's usually this big old peck question, right? G83 that we're going to talk about, all these things. Well, should I peck this? How much should I peck it and all that? So let's dive into this. And this is what I'm gonna let everybody know. I am speaking from experience here. Everybody gets their experience from certain applications. Everybody has different experiences and different opinions. I'm giving you my opinion, my experience, and the experience of our company of how to actually use pecking cycles. So anything that is over 5 times D is usually considered a deep hole. So keep that in mind. So that means with the correct geometry, materials, you should be able to drill without a peck cycle up to 5 times D. Now, there might be some on the call that are listening and sitting there and go, are you kidding me, man? I just drilled a 3 times hole and I broke the drill 3 times and I had to peck it and I had to. You're right. We're going back to the right geometry, the right material for the right application. But usually, 8 out of 10 times, if you're less than 5 times D, if the geometry is right, I'm going to tell you, you don't need a peck cycle. Coolant through drills can drill up to 30 times diameter and beyond without a peck cycle with the proper pressure. So if you're using a coolant through drill, I would not suggest pecking unless there's a problem with the coolant through. And what I'm talking about is proper pressure. Pressure at a minimum should be around 500 psi. 1,000 is preferred, okay? This is very important. So if you're using a coolant through drill, that coolant is really helping. Remember the slide before said evacuate a chip, right? The number one way to evacuate a chip is to put high pressure down at the point. So we're going to get 2 things going on. We're going to cool the point, and we're going to flush those chips up the flute. You still need the point geometry to make the right shape of a chip so you can evacuate it. You can put coolant through on any drill, okay, and not make the right shape of a chip and still struggle with getting the chip out. So when people usually call me as applications and say, hey, listen, Don, I'm using a coolant through drill, and we probably got some application engineers that are on our team that are on this call, and guess what? It's not working. And I have to peck. Well, Part of that is because we're not getting the shape of the chip we need so that coolant can't push it up the flutes and evacuate it. And usually 9 out of 10 times, it's the wrong tool for the wrong application or the wrong speeds and feeds, so we're not breaking the chip properly. Another thing that's very important when you're using coolant through drills to be mindful of is the micron filtration is key to success on the smaller coolant holes. So as we get smaller, we make a drill down to 52 thou in diameter, and I know a coolant through drill down to 52 thou in diameter. And I know there's other drills that actually go even smaller. I actually was working with a customer that was using coolant through drills, and we discovered, and it wasn't that deep, but the coolant, we discovered that the filtration wasn't even coming out the coolant. So we were able to just reduce the cost, not go with coolant through because they weren't getting the coolant out at the end of the tool. It's very important to make sure, and went with standard tools in a Peck cycle, okay? The nut and bolts of it is the next bullet point, not the next slide, because I see that I actually got somebody else controlling the slides here. The next bullet point is the one that people are probably asking, and we can elaborate on. Non-coolant through drills greater than 5 times D will need a G83 Peck cycle or a Peck cycle, okay? We will have to add a Peck cycle. So, series of questions that we're going to answer. Okay, what about work hardening the hole? I hear this all the time, and this is a thing that I've learned when I was younger, actually coming up through the ranks of making drills. You want to stay away from pecking because in certain materials, every time that drill hits the material as it evacuates, number one is you're putting damage on the end of the drill. That's number one. And number two is you could be work hardening the top of that hole every time you're going through, right? Because you really want to think, and there might be some good drill guys out there that are going to say, hey, listen, I want to stay engaged. I want to make a chip. I want to get through there. I don't want to keep pecking that drill. Well, I'm going to tell you, in 8 out of 10 times, you're going to have a choice if you don't use a Peck cycle. And I'm sure there's people out there nodding their head. You can break your drill, or you can make it through a series of holes by adding a Peck cycle. Not every time, but I'm telling you, my experience of running this, without adding a Peck cycle, when you get 5, 12 times D, when you start getting in deeper holes, if we don't break that chip up, remember, we got to make the chip, we got to manage the chip, we got to hold the chip, we got to get rid of the chip. So if the chip is not the right size, it'll clog up in the flutes. If it clogs up in the flutes, we have catastrophic failure, right? Catastrophic. So that's number one. Don't worry about work hardening the hole. What I see is you'll probably not get through the hole if you're going 8, 9, 10 times D, depending on the diameter. Now, this is conducive of the diameter. When we start getting larger diameters, we have a little bit more room. We can manage the chip a little bit better. When we start getting down to that 1/4 inch and smaller, we really have to be mindful of this. So I'm telling you that breaking a tool or breaking a chip, I'm going with breaking a chip. Think about it that way. The next question, should I retract all the way out of the hole? So we're talking about 5 times D and greater. I'm not talking deep hole drills. Let's stop right around that 12 times D, just for grins here, just to keep it on a regular basis, 5 times to 12 times, which is pretty common in drill holes. All right. So should I retract all the way out of the hole? Yes, my opinion is yes. Take that drill, come all the way out of the hole. 2 reasons for this. Number one is if I'm not using coolant through, and this is a non-coolant through drill, I want to get coolant down to the bottom of the hole. Yes, we have flutes that are going to carry it through. It's going to walk through. But if you do have a chip on the end of your point that's sitting in there, number one, the coolant's not going to get past it. And number two is you're not going to get that chip out. So that's number one. Get coolant down to the hole, retract all the way out. Number two, the reason I like to retract all the way out of the hole is because if you do have remnants of chips on the end of the drill, depending on what your cycle is, you're going to take that all the way out of the hole, and the centrifugal force of the RPM of the spindle will help evacuate the chip and throw the chip out. So if you're asking me, my opinion, somebody asked me, instead of retracting 10, 15 thousandths into the hole, or if you're doing just a regular Peck cycle down in the part, I prefer coming all the way out of the hole as long as you're not in a deep hole situation. So to spot or not to spot, there's another question. Boy, we got all these Shakespearean questions today. So to spot or not to spot, that's the question, right? There's another question. Should I spot my holes? Should I not spot my holes? So spotting is necessary when you have some of the following conditions. If you have the right point geometry on your drill and you're within the times diameter that you want to go through and your conditions aren't like these, I would say you don't need to spot all the time. And number one is an irregular or angled surface. If you have some kind of angled surface, and I'm not talking where you're going to use a flat bottom drill. We're not talking about flat bottom drills because we can get into a whole conversation. I'm talking if you have an irregular surface that's a little bit rough, you're going to want to use a spot. If you have scale on the surface or a rough face, if you went in there with a rough face and maybe you ran it faster because it's not critical what the surface is, that apex or that point of that drill could move off. So you want a spot. You want to put a spot in there in proper point geometry. If the drill you're using, whether it be high-speed steel or carbide, is not specifically or material specific for that material, then you're going to want to spot. And I mean if it's not self-centering, which means that split point, which gives you an apex. Now here's the thing, you're going to see two different carbide drills. Usually some are split, but other ones will have a 4-facet grind on them. I'm going to tell you right now, if you use a 118 drill or a 140-degree drill and it has a 4-facet point, those 4 facets, the 2 facets come on center, that will create an apex and will help self-center. So those drills can self-center. So it's not that straight chisel edge I talked about early. A 4-facet carbide drill will self-center itself because it has a little apex right on the end of it that kind of dives in your material. Split point drill will do the same thing. So if your web is too large, that thing's going to wander and walk like crazy. And if it's not carbide, it's really going to make a wobbly hole. And if it is carbide, it could possibly break. Inconsistent hole locations. Let me explain what this means real quick. So if you're drilling holes and you are getting inconsistent hole accuracy when you're checking them, you don't just drill a hole and assume it's good and you check it. Spotting might actually help give the consistency in the hole. So when you're looking at using a spotting drill, the key to using a proper spotting drill is finding one that has a flatter point angle than the angle that's on your drill. You can look at the picture at the bottom of this and you can see a proper spot angle. So if we're using a 140-degree drill point or a 130 or 35-degree drill point, we want to go with a flatter angle. So we're going to pick a 140-degree spot or something that has a flatter angle on it. 118, you want to make sure it's flatter. The reason for this is we don't want to, number one, hit the outside of the cutting edges, especially on carbide, because what you'll do is you'll start wearing that out and you won't actually dial in on the center of that spot. When you use that spot, what you're doing is pre-starting that hole for the drill. So it's important to use a spotting angle that is flatter than the one you're actually using. So that being said, can you drill with a 90-degree and go in with a 140-degree drill because you want the 90-degree chamfer left on there? Absolutely. Are you going to run in problems long-term? Yes, it's all about long-term, right? We're drilling 1 or 2 holes. Man, I'll tell you what, go to your toolbox, open it up, find out what drill you got in there, put it in, and drill your hole. I get it. We all get it. We all understand it. But if you're trying to get in a production environment, you want to go with a flatter spot than you're actually using. So deep hole drilling with pilot holes. It looks like I got control back, which is pretty good. I see my moderator looking at me, so that's nice. I got control back. Don't know how it happened, but that's good. So deep hole drilling. So we're going to stay on this real quick, and then we'll do tips and tricks because I know we're a half an hour in. So if you're deep hole drilling, there is a process for deep hole drilling. When is it a deep hole? Usually when it's greater than 12 times D. That's what we look at as a deep hole. When you want to kind of look at a pilot hole. A pilot drill is something we're going to use, which is usually 1.5 or 3 times D, or you can literally use something that's maybe even 5 times D that you have that's of the same diameter of your finished drill. Real simple to use a deep hole drill, but very important to use this. Number one is deep hole drills are probably going to have coolant through. They should have coolant through. It's going to give you the best results. And remember, if they don't have coolant through, think about pecking. Okay, very important. First thing you're going to do is drill your pilot hole. you're going to drill that 1.5 times D. You're going to drop your drill into that hole. So if you're greater than 12 times D with your drill, drop your drill into that hole at a low RPM. Make sure the spindle is spinning. 250 to 500 RPM is good. The good thing about running 250 and 500 RPM with a deep hole drill is, I'm telling you right now, if you're over 12 times D, you can literally look at the drill and see if you're running out. That's how much that thing will wobble if it wasn't made correctly or if your collet's not good. Drop that in the hole at 250. When it gets down in there, turn your coolant on in the pilot hole, increase RPM to recommended, drill the hole and retract all the way up to where your pilot is, 1.5 times D, or where the pilot is. Reduce your RPM, come out of the hole, turn your coolant off, and then repeat the process for the other holes. Very important, because what you get is you get a drill that's spinning around at high RPMs depending on your material. There's a lot of centrifugal force and stuff going on, and that drill wants to whip. So it's very important to do that actually with a pilot drill. Tips and tricks. Let's finish with tips and tricks, and let's get into thread milling. I love these people probably sitting here going, hey man, I'm a thread milling guy. I don't care about the drills. But I'll tell you what, you can't use thread mill unless you make the holes. So there you go. I got you. That's why we started with the drills. Nice little combination. So double margin drills, right? We have drills that have a margin on them. Usually if you look at a drill, there's one margin on there. I'm going to give you a tip on a double margin drill and why you would want to use a double margin drill, which is basically a margin or a cylindrical margin on the front of the drill. And then on the back side, there's another margin. Sometimes there's even 3 margins. Why is this good? Well, number one, you can use a double margin drill kind of as a reamer. So make sure you're looking at your prints. When you're quoting jobs, that print comes in, take a look at the tolerance on your hole, because sometimes engineers won't specify it has to be reamed, but you're looking at it like, oh man, this is too tight for a drill. Maybe it's 5/10. You can get away with a double margin drill. Why? Because it'll make a round hole and it'll make a hole on size. That back margin actually burnishes the hole and makes it act a little bit like a reamer. Great for interrupted holes. If you have an interrupted hole, a double margin will stabilize itself in the hole. So if you drill the first section of that hole and then go through another interruption to drill another one, guess what? The double margin on the first section of the hole is going to act like a bushing, like it's in a bushing, and it's going to self-center itself as it breaks through the other hole. So if you are doing interrupted cuts, look at double margin drills as an option to actually run when you're doing interrupted cuts. Rounder holes versus single margin, like I said. And here's the downfall, okay? If you're thread milling the hole afterwards, if you're tapping it, be mindful that a double margin drill, and I've seen this happen, can work hard in the hole. It can work hard in the hole. So because you're burnishing that hole, you're making it rounder. The back margin is cylindrically ground. So there's no relief on each one of these margins on a drill. It's not like an end mill. It's not eccentric. There's no relief on it. It's cylindrical ground. So it will rub on there. So be mindful if you're drilling a hole, you're using a double margin, you're just breaking end, you're breaking taps, you're breaking thread mills, it's not working. Think that that might be work hardening the hole. And work hardening the hole is a big issue when you go to tapping that we'll talk about in a little bit. Lip correction or dub on the cutting edge, right? So there are certain things you can do to drills to take rake out of the cutting edge. When you're running a drill in softer material, be mindful that that drill is going to want to grab. And especially in plastics and brasses and soft aluminums and stuff like that, if you've ever used a drill, a hand drill in aluminum, sometimes that drill is going to want to grab and pull your hand. You can put a dub on there in softer materials or a lip correction, which makes the edge stronger, and it takes some of that rake out of the cutting edge. This is something to think about if your drills are grabbing. We can make recommendations on that too as well. Honed cutting edge. There's a lot of drills out there that have a true honed cutting edge, where what I'm saying is instead of just breaking the edge or edge prepping it, they actually have a ground hone on there. Makes them really strong. It's great for hardened materials. So you will see a hone on really good tools on the cutting edge. And speeds and feeds. One thing I wanted to put here on tips and tricks. It's all about the chip, right? We said we got to manage the chip. If you are drilling a hole, whether it be in a mill, in a lathe, with a hand drill's a little bit out of it. But if you're drilling a hole and you just can't get the chips manageable, a lot of materials don't want to break a chip. Depending if it's 300 series stainless, it doesn't want to break a chip. Increase your feed. Your feed will help break a chip. Okay, if you feed it faster, now there's a limit. Don't break your drill. And I'm telling you, if the chips aren't breaking, you're not feeding it fast enough. Feed the drill, it'll curl the chip, it will break the chip. You watch, go back to your machine today, go and run it slow, get a long chip, start feeding it faster, and watch how those chips change. Those chips will start changing before your eyes and get smaller and get manageable. That's it on drills. So thread milling, let's jump right into thread milling because I want to leave some time for questions here because I love answering questions and you folks really have some good questions. We're going to talk about 3 types of thread mills, right? Single form thread mills, tri-form thread mills, multi-form thread mills. Not only are we going to talk about the advantages and disadvantages, but I'm going to give you a couple little tips on how to use these things, okay, as we run through them. So let's talk about a single form here real quick. Single form thread mill. One form on there, 60 degrees on the pitch because that's what we're running for threads. Not all 60 degree. There are some 55, British Standard 55 degree. Acme is a little bit different, but we're talking about UN threads or metric threads with a 60 degree. What are the advantages of a single form? Why would you go with a single form? A lot of advantages. Best depth to diameter ratio, up to 6 times diameter. So what I'm saying with a single form thread mill, you can get down pretty deep and create threads in a pocket. That's about one of the only thread forms that's actually going to allow you to get down there and actually do that. Least amount of tool pressure. We have one form. We have one cutting edge that's in the material. That's why we can get down deeper. We don't have that tool pressure. That pressure is not there because we have one form. So we cut a lot freer with this tool. So we can take minimal spring passes with this. Spring passes, we're going to get into that. Everybody knows what a spring pass is, especially if you're thread milling. I guarantee everybody on the other end of the line is going, yeah, spring passes. Now you're going to say, hey, Don, teach us how to get away from spring passes. Sorry, it's springtime and you can't get away from spring passes. That's it. There's no way. Actually, you can get close, but it's hard to do. It's part of the common practice in this, but we'll help get you there as much as possible. You can do right hand and left hand threads with a thread mill, single form, multi-form, and tri-form. You can do them with all 3, but this is an advantage. So if you have a left hand and you have this tool in your toolbox, boy, you can run it for both ends. You don't have to go and buy another tool. Internal and external threads with the same tool. I don't need another tool. And you can machine multiple pitches with a single form thread. You can't do it with multi-form and tri-form, but with a single form thread mill, you can do multiple pitches, which means if your diameter is within your minor of your hole, you can actually run a 32 pitch. You can run a 24 pitch, depending on what you pick. You can run a 20 pitch. That's the threads per inch. That's TPI, threads per inch. That's your pitch that you're actually running. You can run that. That's why I like a single form thread mill. Not only the fact that I can go deeper, but I can use it for multiple pitches. The disadvantage and the main disadvantage, it's slow, right? It's single form. You can only do one thread at a time. So if you have a lot of threads, it will be slower, but it is very versatile. It's a very versatile tool. Triform thread. So we have a triform. A lot of people have triform thread mills. I'm going to talk about our triform thread mill. I'm going to tell you what's great about this one, but I'm also going to tell you what's great about a triform thread. Number one, this one is left-hand spiral, left-hand cut. And we'll get into why that makes this one great, because I'm an old school machinist programmer. I had my own shop for 10 years. I know I started Precision Twist, but I've used all this stuff. So I know what I like and what works for me. So you're using an MO4 on the spindle versus an MO3 right away. So if you buy this tool, don't spin it on a M3, and make sure it's going M4, which is opposite way. So it has the ability to cut right hand threads from the top to bottom. Okay, so why is that critical? Why do we like that in some cases? I'll give you an advantage right away. Number one, if you are programming longhand and you're actually doing it with GO3s and GO4s, which is your circle interpolation, right? Yes, I do know G&M code, so I haven't done a lot of it lately, but that's where I started on the machine. So if you're doing a GO3 or a GO4, with a thread mill, the key with a thread mill is you want to arc in and you want to arc out. Okay, so programming an arc in and arc out sometimes can be cumbersome. It was for me. That's usually when you get in, you just slam that thread mill into the side of the wall and you go from there. But with this tool, you're starting at the top of the tool. So basically what you're doing is a helical ramp, a helical interpolation with the pitch, whether you buy a 20 pitch or a 32 pitch, from the top of the tool, of the top of the part. So basically come down on Z, move over, helical ramp all the way down to the bottom of the hole, come out and come out of the hole. So the programming is a lot easier with this tool. The fact that it has 3 teeth runs a lot faster in a single form. It's the strongest tool that you're going to have in the arsenal. So it's designed for harder materials because you can get a thicker web in there. You can get stronger material in a triform. You're starting at the top of the tool. So this is your winner for a work hardened hole. I'm telling everybody right now, this triform, if you've drilled a bunch of holes and you don't know that you've work hardened them, but you can't get a tap to work and you can't get a thread mill to work, I'm telling you right now, and you can use my name, Don Grant, Harvey Performance Company, National Application Engineer. This tool will get through that thread. I've done it several times. So if that hole is just giving you a lot of problems, take a look at a triform thread. It will really get you through the hole. It's limited tool pressure because it has 3 teeth versus multiple, and it's faster than single form. So what are the disadvantages? Well, slower cycle time than a multi-form. It's a lot stronger. There's a lot more advantages, and it's limited on the diameter to axial because we do have a little bit more tool pressure on that. So it is a little bit limited. So we're going to get to multi-form now. Multi-form is pretty common here. We offer an extensive offering of multi-form tap or thread mills, and trust me, more than I've ever known from the past. If you ever look at our arsenal of thread mills, we have long thread mills, MPD thread mills, coolant through thread mills, every different option that you would want on pitch as far as that goes. But what are the advantage of using a multi-form thread mill? Fastest way to mill threads. Now you notice I said fastest way, got a real good play on words, right? To mill threads. If you're going to mill threads, this is one of your fastest ways is to use a multi-form. The teeth are throughout the entire length of cut. Okay, that means if you're running a 5/16 thread depth, you can get there with one arc pass to create the thread pitch. Drop down to the bottom of the hole. Right hand thread is going to be from the bottom up. You're going to drop down to the bottom of the hole. You're going to arc one complete revolution or maybe a revolution and a half. You're going to come up the thread pitch. You're going to come out of the hole. Okay, can run in hardened materials where a tap could break. So this is a good solution where your tap could probably break. You can run this in harder materials. Multiple diameters with same pitch. So if you have a 20 pitch, depending on what your diameter, it might not just be quarter 20. We've all seen engineered print. This might come, you might get something that says 5/16 20, or you're running up with 3/4 20, where they want a 20 pitch on a 3/4 diameter. If your diameter, your axial, is within that thread mill, you can use this thread mill for any 20 pitch. If this is a quarter 20 thread mill, you can use it for beyond as long as your axial length is good. Disadvantages. Spring passes sometimes required. And I put the word sometimes in there, but I'm telling you, most times required, okay? Because what you get is you have a lot of tool pressure. And if you run a go, no-go gauge, and I'm sure there's people out there, maybe a couple thumbs up in the chat there if they say they always have to run spring passes with their thread mill. This is really going to be limited to how deep you go with that thread mill. You start getting really deep with thread mills, and some people make them, and we can go up to 3 times deep. The deeper you go with that thread mill, the more tool pressure you're going to get at the bottom, the more it's going to flex. From with it in with a go, no-go gauge. If your go gauge is tight or loose at the bottom, that's when you're going to want to take some spring passes and kind of do that. So great tool, great in your arsenal. Now, number one, disadvantage. Everybody can sigh at home right here for this is no broken taps in your part, right? Largest advantage to thread milling. This is your biggest advantage right here. The last operation you're usually doing on your mold, your part, or whatever is putting your threads in there. Breaking a tap off in your mold, in your material can cause catastrophic headaches, shorten your life, lose your hair, whatever you want to say. I mean, that's what's going to happen. Is it's almost worse than kids sometimes as far as that goes. It's more upsetting. But this is key. This is why we want to take a look at thread mills. You really want to look at a thread mill over a tap to eliminate these issues, and it's huge because you break a thread mill off in a hole. Guess what? You put a new one in. You pick right up on the thread. You touch off on Z. You're good to go. And you're making threads again. So this is really critical and a big a positive here. So let's talk about programming thread mills. And I know we're about a quarter to the hour right now, and I want to leave about roughly at least 10 minutes to go through this. So we're going to run through the next 5 minutes, but if there's questions on this, we'll be sure to answer them. So programming thread mills. Inside and outside threads need adjustment for feeds. We've probably seen this. If you've done a lot of thread mills, we have a calculation, and I read it the other day, and I need and I've read other people's calculations, and I think you need a degree in physics and whatever to understand it and everything. It does get simpler the more you do it, but I'm going to give you an easy way to do that. Reduce your feed by 15 to 20% from recommended for inside threads. Increase your feed by 15 to 20% for recommended for outside threads. Why is that? Well, if you look at the picture on the left, if you're doing a 20 thou radial step over, and you're actually cutting that, because of the diameter of your inside threads, your actual angle of engagement or the actual radial on that angle is greater. So when it's greater, we want to slow the feed down in order to get the performance out of the thread mill. So when you're on an inside arc like that, you're going to have an exaggerated radial step over. Therefore, you need to reduce the feed. An easy way to do is reduce it by 15 to 20% from recommended inch per tooth. If things are going well, you can easily bring it up. There's a window on everything. We put windows on everything. We're giving you safe recommendations. You can bring it up. But a smart way to get tool life is keep in mind that your inch per tooth or your engagement that's on that tool is going to be greater. When you go to the outside, it's the opposite. The angle of engagement gets less. So we're creating chip thinning there, and we're rubbing more. So you want to increase that feed from recommended to get the chip up to where it needs to be and the angle of engagement so that you can get optimal performance. So think about this slide here with an end mill. I want everybody to think, anybody that does any milling. Same thing with an end mill. When you're cutting with that end mill, you're in a circle. If you're tricoiling, you get more of an angle of engagement. We do have another presentation on that. Be sure to go back to our YouTube channel, take a look at that, and it'll kind of explain some of that with an end mill. Programming thread mills. Again, let's talk about recommended radial passes for a thread mill and understand what I'm talking about. This isn't law. I'm not telling you that you need to do 4 passes with a thread mill depending on material. But remember, we have a lot of conditions here. We have lengths of cut, we have diameter, we have core thickness, we have thread passes, all that. So all this is going to take into effect. So we're not giving you specifics to tell you, hey, you're running 4140, you're running a 1/4 thread mill, you're going down 5/16 in diameter, bam, I can give you those specs. I can tell you right now to run on those. I'm giving more of a generalization of how to look at this when you're doing this. So your radial passes, which means your step over when you're doing these passes on a thread, will always be contingent on the material you're cutting. As your tool gets deeper or radial engages more on your threads, the threads, the engagement on your tool will get greater, okay? So reduce the last couple of passes to reduce the engagement on the cutting teeth. Let me explain what that means really quick, okay? So when you do the first pass, if you're breaking it down to 4 passes, obviously because it's 60 degrees, you're not engaged all the way on those 60 degrees. You're just touching on the end of the thread mill, which is light engagement. It's not a lot of pressure, and that tool can take it. The example I put here, if you're doing 3 rough passes and a finish with a thread mill, which can be done depending on the material, you can do 1 pass, there's 2 passes. Be mindful to break up those passes. Do a 40% on the first pass, a 30% on the second pass, a 20%, which is your radial step over on the third pass, and then maybe a 10% on the last. It will minimize the force. That last pass of 10% is putting the most amount of force on your thread mill. So don't make it 40%. if you can get away with it. And then if you have to add a spring pass, add a spring pass. Now I gave you 4 passes. I did show a little chart here that we have recommendations for this with easy machinability, moderate. This is on Harvey Tools webpage. You can find this, you can download it, you can take a look at this. It's a great recommendation for these. But you have to be mindful of those radial stepovers when you're actually cutting with Threadmills. Finally, we're going to finish with Threadmill tips and tricks, just little things just to throw out there to see if it kind of helps, and then we'll answer some questions here. But use the least amount of thread possible if not specified on the print, down to 62% thread or even lower. This is a big one. So engineers, and I'm sure there's engineers on this call, and God bless you, I love engineers. I really do love engineers. I'm saying that really because you can't see me, but sometimes some engineers tend to put a thread percentage on a print that maybe doesn't need to be there. But if it's on the print, we got to go with it. So we know when we tap or when we thread mill, we're trying to get a percent of thread, right? Normally 70-75% of thread is where we want to be, okay? Or is where somebody's going to put on a thread. Usually, and this is not, it is proven back, anything greater than 55% thread is usually the same as 75% thread. So what I'm saying is if the thread depth is not specified out, I would start at a 62% thread versus a 75 or 80 because your tool will last longer. And you would be amazed on how to get your tool to last a little bit longer just by adding or taking away some of the material. Now your thread depth is generated by your hole size, just so everybody knows. So whatever you drill your hole size, what I'm telling you, if that's 75% thread, and there's calculators for that, is make that hole bigger. Okay, if you can get away with it, if it's not specified on the print, get the 62% thread, it'll give you more tool life. That's a nice little tip. This is very important to keep in mind if you are tapping. I'm just throwing that out there. We don't sell taps yet. I'm just saying, but if you are tapping, keep in mind your hole size is very critical to tap life. So if you can get that whole thread percentage lower, do it. Coolant through on multiform thread mills adds about 30% to the tool life. It's evacuating the chip. We actually offer coolant through thread mills in our catalog. It's something to think about, and it's something that a lot of people don't look at, but coolant through thread mills will help. So programming, right? CAM packages help create thread mill programs. We can do it longhand. We can G&M code it. And I'll tell you what, when I was G&M coding thread mills, I was so lazy. I didn't do an arc in and an arc out. I dropped down in my hole. I came over an XY straight line. I engaged in my material and I circle interpolated out, which some of you guys might be doing. And you're probably having good success with that. It will fatigue tool life, which is why you want to arc in and arc out. There are several threading programs within your Fusion 360s, your master cams, your Esprit, Gibbs cam, solid cam. I don't want to discriminate. They're all great cam package. Get your hole, put it on your plot, create a thread mill program, put in your information. It will even let you break up those passes too as well. Remember how I said 40, 30, 10? In a blind hole, make sure there's adequate clearance at the bottom of the hole, okay? 15 to 30 thou depending on the pitch diameter. Even though it's a thread mill, it goes to the bottom. Please put some clearance on the bottom if you can. If it's allowed on the print, clearance will definitely help with the chips, the evacuation. You still are making chips with a thread mill. And chamfer your holes prior to cutting your threads versus after. This ensures a good, clean start for your fastener. It's just common practice. Chamfer all your holes. Go in there, drill your holes, chamfer your holes, go in with your thread mill. I'm going to tell you right now one other tip. Like I said before, I just want to reiterate this. If your thread mills are breaking, okay, if your taps are breaking, if your single form thread mills are breaking, okay, I happen to hang out with thread mills on the weekend. They're kind of friends of mine. Don't blame the thread mills. Blame the drill, okay? 9 out of 10 times if your thread mill and your taps are breaking, it's the drill's fault. You're work hardening the hole. So take a look at your drill application. You can fix that work hardened hole by adjusting speeds and feeds or getting the right geometry on a drill, and therefore your thread mill, your taps will have a better time to sustain and live. I'm going to leave it open for questions, but what we threw up here, Jeff Rossio, our digital marketing manager, You can take your phones, put them up here, scan. It'll take you right to the Threadmill offering that we have on Micro 100 and Harvey Tool. You can take that, you can download it, you can take a look at those offerings. If you have any questions about that, this is a nice feature. Go ahead and do that. And with that, I'm going to turn it back to Jeff Rossio. I'm going to say thank you, and let's answer some questions.
All right. Thank you, Don. We do have some questions in the chat. Like Don said, if you're interested at all in just checking out the Threadmill offering, grab these codes. It's as easy. If you have a smartphone, just open your camera. It'll bring you right to the web page. So that's a nice place to start if you're interested in looking at some of the tools that were talked about today. So a couple questions here. First one, do you do degressive passes to maintain a constant load when thread milling?
So degressive passes on the radial? Yes. Yes. I mean, you can do that to modify the load on the Threadmill. I'm trying to understand if I understand it. Degressive passes. So basically on the radio, is that kind of just going through the question where I said 40%, 30%, 20%, and 10% as far as that goes. So if you're making a thread with a thread mill, if you're using a multi-form thread mill, you want to stay engaged in the material all the way. So you're going to go down, you're going to stay in there. So you do digressive passes. Yeah, I think that's what that is. Digressive passes on the radio, just like we explained. Yeah, 100%. Yep.
Okay. So question here on why is bottom up better than top down when thread milling?
Well, first of all, it's right-hand thread, left-hand thread, right? Mm-hmm. So bottom up, it's a left-hand spiral, left-hand cut. So in order to generate a right-hand thread, we have to cut from bottom up to climb mill. And so we're trying to climb mill with the thread mill. I should have brought that in. So climb milling is key also with the thread mill. So do a left hand, if you were doing a left-hand start thread, you would go top bottom.
Okay. And then when we list the diameter of a thread mill, do we take the crest on the tool into account?
So we do. I mean, all of our thread mills are all calculated with the crest involved. Yes, absolutely. The crest and the root, where the diameter of the thread mill. So if you look at the diameter of the thread mills that we list in our catalog, it'll be a 1/4-20 thread mill, but we'll give you the diameter of that. That's with the crest of the thread mill. Yes, it is taken into account.
Great. We got some more questions coming in here too. They're coming in rapid fire now, so this is good.
Yeah.
If you guys have questions, this is a great time you got one-on-one access to Don here. So Rob Lemon asked, he said he's been running into a lot of copper applications lately. Mm-hmm. Do we have deep drilling options for copper?
Well, here's the thing. We have deep drilling options that will, now when you say deep drilling, I'm going 12 times D and over. So we go to 20 times D on our coolant through drills. Will those work in copper? Yes. Are they designed for copper? No. Can we get them to work? Yes. So we do have choices for copper for deep hole. Okay, but depending on how deep you're going, I would evaluate that process and see if it's the right application. One thing you're going to find out with me as a national guy and as our local guys, listen, call us. We'll steer you in the right direction. We're application guys, so we might be able to find you a source that might work a little bit better for us for a specific material, which means if it goes deeper than what we offer and it's material specific, we do have great relationships with obviously our competitors to actually point in the right direction. So we do have copper options depending on what you're doing. Yes. Stringy chips, by the way, pain in the butt, hard to break.
Yeah, I'm sure. So yeah, if anybody ever does have questions, please give us a call, give your local guy a call. They'll be able to help you out, make something happen, no matter whether we have it or not. There's options. So a question here from Jonathan Schneeman. What would be a good resource for Peck depths by drill type and material? Do we have anything like that?
We do. Actually, we just did an in the loop. I just saw it the other day. There's an in the loop that you can go on that has Peck depths on there. Okay, I did review it yesterday. Okay, and it's in the ballpark depending on what you're doing. Remember, this is a generalization, and pecking, when it comes to pecking, depending on what tool you're using, and how deep you're going, it is. I'm going to say it is a science. And I have solved a lot of problems. And let me just point this out here. If your drills are breaking and it's a non-coolant through drill, start messing with your peck. I'm telling you right now, 100% of the time, if your drills are breaking and it's non-coolant through, start messing with your peck. One thing I wanted to bring up on Peck, Jeff, really quick. If you're going 12 times D, you are going to adjust your peck as you get deeper in the hole. So even though you might get away with 1 times D for 5 times of that depth, when you start going 6 to 8 times, go to 50% of the diameter. And when you go all the way down to the bottom, you might need to go 20% of that diameter. It's a lot harder to get those chips out at the bottom. So keep that in mind too as well. But I'm going to tell you, if your drills are breaking, it's because of the chip management and the pecking if it's not cooling through. And we can fix that. Give me a call. We'll fix it.
Absolutely. Question here from Dan Hewitt. When drilling, you had mentioned that over 5 times D, all the conditions are met. It can be done with one peck. So if the hole is greater, what depth is generally recommended after the first peck of 5 times D?
Me personally, depending on the material, I'm going to say 50% of the diameter. A lot of people are going to say 1 times the diameter. Man, I like 50% of that diameter. So basically, if you're using a 1/4 inch drill, peck that thing at 125. You might even need to go less, but I'm going to tell you something. Machines are made to peck. I know it sounds a little bit rough. And if you're running the right speeds and feeds on a carbide drill, it does not slow you down that much. So if you're pecking in a hole, reducing that peck, I know it does add some cycle time, but like I said, what's the alternative if you're breaking drills and if it's deep hole? So I would tell you right there, over 5 times D, depending on what the material is, what the chip looks like, at least 50% of that diameter. And then if that's a 12 times D drill and you're going down that, you might look at 20% of that diameter to actually get through it. And if you're doing micro drilling, you're starting at 20% of the diameter without cooling through.
Awesome. So right about 3 o'clock now. I don't want to hold anybody too long, but if you guys do have more questions, I'll leave an extra minute here for you to get those questions in. We had some great questions, so thank you everyone for participating. Like Don mentioned too, we have our In the Loop blog. So if you go to any of our websites and go to resources, you'll see In the Loop blog under the resource drop down. If you head over to the blog, there are a ton of posts on spot drilling, drilling, peck depth, thread milling, tool selection, all kinds of good stuff over there. Outside of drills and thread mills, there are literally dozens of posts. So definitely another good resource if you want to keep reading on this. And like Don said, give us a call anytime, and our guys are happy to help out. Yeah, it looks like no more questions there, but so we'll sign off here. Thank you everyone for joining us again. Hopefully we'll talk to you soon, and stay safe out there.
Absolutely. Take care.